I'm 𝘁cie from Politecnico di Milano, and today I would like to introduce a new topic in the lectures of the AI-SPRINT project, Neural Architecture Search. Within the AI-SPRINT project, we have introduced a design framework for AI application in the computing continuum and a runtime framework for this application. As we know, the machine learning part of an artificial intelligence application is a minimum part within a bigger ecosystem which goes from configuration to servicing, with the data collection, features extraction, monitoring, and all sorts of tools in the middle. Today we will focus on the machine learning part. In particular, we will introduce the idea of neural architecture search as a way to design AI models in an automatic fashion. The model we will talk about today are computer vision model. Computer vision model, they take an image as input and they can perform different tasks. For instance, they can classify whether there is a cat, a dog, or a duck in an image. In this case, we talk about multi-label image classification. They can classify the whole image. In this case, we talk about image classification. We can detect where in the image we have one specific object, for instance, like in the picture where we identify where the cat is and the dog is. And finally, we have another problem which is called image segmentation. In this case, we go at the level of a single pixel and we identify for each single pixel whether this belongs to a cat or dog. Why all these applications are relevant? Well, think about finance and some insurance company. If you have a way to perform a visual task where you can use computer vision to examine a damage of a vehicle, you can streamline the insurance process by having an artificial intelligence expert to do the analysis. In healthcare, think about detecting breast cancer. In this case, we have an application where an AI system is able to detect whether in a mammography you have or not a lesion. In manufacturing, for instance, you have a monitoring system where you can detect who is wearing a helmet to increase the safety of workers on the field. And clearly, we have retail application. For instance, we could detect whether a person, a customer, is interested in a given item in a store or whether it has issues in interacting with the store element. Classic example of computer vision AI applied to autonomous driving is the capability of future autonomous vehicle in detecting whether there is a car, a pedestrian, or an obstacle on the way. Agriculture, another field where you can use a computer vision system to predict the yield, to understand whether there is a particular stress, and to suggest the farmer of the future how to apply nutrients to their field. Other application, advertising. In this case, you could customize the advertising by understanding who is looking at the advertising, how these people are interacting with this. But what has started all these applications? What has made it possible to have such a large variety of models? Well, we can say that everything started with ImageNet. ImageNet is a collection of images where we have a task which is classifying what is the item in an image. Here, an example of the application. So let's look at the task of recognizing what is in these pictures. So for instance, in the first one, we have a mite. This is the object in the picture. And below, we have the output of a model which was proposed in 2012. This model is called AlexNet and is depicted on the bottom left of the slide. As you can see, when it's prompt with the image of a mite, the model believes there is a mite, a black widow, a cockroach, a tick, or a starfish. It means that between the first top attempt, at least one matches the right target. An example is the container ship, the motor scooter, the leopard, mushrooms, Madagascar cat. So these are some of the examples. Here, other example where the model sometimes is successful in detecting either a koala or a tiger in the picture. But in general, it turns out that it will have a mistake only 16% of the time. It means that more than 80% of the time, the right class of the image will be correctly predicted by this model. Now, this model was proposed in 2012. After that, we have seen the accuracy of these models increasing more and more. So, for instance, if AlexNet, which was the 2012 model I was talking about, was correct almost 55% of the time, then it has been improved by GoogleNet, VGG, ResNet, Inception, and so on. What is the difference between these models? Well, we have a lot of difference, in particular in the complexity of this model. Well, I will not get into the detail of this picture, which is not important. This picture is useful to me to show that there are different possible choices of models, each of them with a certain accuracy or a certain computational cost. If we go back in the year to 1998, convolutional neural networks, which are the basic model for image understanding, were very simple. But then AlexNet increased the complexity of this model in 2012. After AlexNet, the year after, we had an even more complex model, which is called VGG. And after that, we have GoogleNet. You see that the more you go with the years, the more the complexity, but also the higher the performance. If AlexNet was wrong 16.5% of the time in 2012, GoogleNet in 2016 was wrong only 3.1% of the time. Consider that a human at the ImageNet task is wrong 5% of the time. The complexity has grown from few layers like 5, 10, 19, 22. Nowadays we have network with 152 layers. Almost impossible to design by a non-expert developer. And beside the size of the network, we have different components for this. So we started with the classical convolution, then we have the residual blocks. After residual blocks, we have the inception blocks, and so on. For instance, in this case, you see an example of the inception block of ResNet. If you look at the panorama of possible combination of these blocks and the neural network, you see that we have an overwhelming complexity in the kind of model that we can develop. Here comes the problem of automated machine learning. We know today that to solve complex vision tasks, we can use convolutional neural network. We know that there are different architectures that can solve a task, and some of them are more costly in terms of computational power, some others are more efficient in terms of power. Can we automatize the workflow of developing this model? Traditionally, what an expert would do is to define the problem, collect the data, pre-process the data, train the model, evaluate the model, and cycle through all these operations. This is very costly in terms of time, but also it requires a high level of expertise, which usually is not available in a common company. What automated machine learning does is to replace the pre-process, train, and evaluate part of this cycle by a computer program. So again, once we have defined the problem and collected the data, this automatic machine learning tool will cycle through preprocess training model to mimic a human expert and develop autonomously a new model. This idea is a sort of automated lab experiment where the user provides the data, what are the target metrics, what are the constraints in terms of time and cost, and the machine performs a lot of experiment by testing different combination of features, algorithm, parameters, and then at the end return to the user what are the best combination for the problem that the user has specified. This can be done also at the level of neural networks. In particular, the user does the data preparation, collecting, cleaning, and augmenting the data. Then we have a part which might be there of feature selection, extraction, and construction. And then we have a search space that a model analyzes. When part of this search space is represented by deep neural networks, for instance, convolutional neural networks, recurrent neural networks, and the algorithm, what it does is to find what is the best neural network architecture, the best parameters, and the best hyperparameters. Well, this optimization process is called neural network architecture search. In short, neural architecture search. In this part of the tutorial, we have introduced the idea of neural architecture search. We have seen that different solutions exist for a neural network for a given problem. We have seen that you need an expert to find a proper architecture, but we know that this expert can be replaced by a program, and this special program is called neural architecture search. In the next tutorial, we will detail the architecture of a neural architecture search engine, its functioning, and we will provide some of the examples.